Hi everyone, welcome to today's workshop covering the foundations of statistical modeling. We really appreciate you guys all being here. We have a lot of content to get through, so for the sake of time, we're just going to start and let people trickle in. So my name is Jamie Samper. I'm the Associate Director of Data Computing and Research Support at Analytics at Wharton.
I'm a data scientist at AEW.
So the objectives for today's workshop, actually before we get into the objectives, I kind of want to do a temperature check of everyone in the room. Who here has taken at least one statistics course before? Multiple statistics courses? Anyone familiar with the terms regression? Hands up. Okay, how confident do you feel interpreting the outputs of a regression? All right, perfect. This is exactly the audience that we're looking for. Okay, great. So learning objectives, what are we going to not try to accomplish? We're not going to be writing formulas in here. You're not going to walk out of here and be like, I can write the equation of a linear regression. That's not the goal. The objective that I want you guys to all walk away from this workshop is to be able to understand the high-level processes that underlie statistical models. So you'll be able to answer the questions of, why do I use a given model? And if I'm using this model, what do I expect to learn from it? I want you to be able to understand the high-level processes behind things like machine learning models and AI models. The models that we're going to be going over today kind of set the foundation for more advanced modeling techniques that can be considered machine learning that are also used in AI tools. And so I'll try to highlight that throughout the workshop where it comes up. And hopefully the goal is that you'll leave today's workshop feeling comfortable about engaging in technical conversations. You'll be able to be in a room where people are talking about what model to run, and you'll know why they're making that decision and what they expect to learn from a given model. So we're going to start off, simplest form, a correlation. Everyone in this room should know what a correlation is, right? So for every type of analysis or model that we're going to go over, I'm going to have these three main questions. Why would you run this analysis? What do you learn from the output? And how do you interpret that output? So for correlation, starting off easy, everyone knows this. Why do you run it? To see the relationship between two variables. What do you learn from it? You learn the strength of the relationship between two variables. So let's say variable X and Y. And so what would we talk about when we say the strength of a variable? So as one variable increases, what do you expect the other to do? To increase or decrease? When you're interpreting the output, you want to look at the correlation coefficient and you want to look at the p-value. The correlation coefficient, you're looking for two main things. The sign, so positive or negative, and the actual value. Correlations range from 0 to 1, where higher values indicate a stronger relationship, lower values indicate a weaker relationship. So the examples you see here, if we have a 0.9 positive correlation, we can interpret that to be a strong positive correlation, so that as one variable goes up, the other variable goes up in a similar type of fashion, kind of in parallel. A negative 0.1 correlation is a weak negative relationship. Negative meaning as one variable goes up, the other variable goes down, but the association is quite weak. So these two variables are not growing in parallel with each other. So I keep saying the word variable. Let's just align on variables and what type of words that I'm going to be using throughout the workshop, and that you'll be able to reference back to what I mean by those variables. So when we're working with models, especially predictive models, we have independent variables and we have dependent variables. The independent variables are the causes or the predictors. When you get into more advanced modeling techniques like machine learning models, they might refer to independent variables as feature variables. Then you have the dependent variables. These are the variables that you are trying to predict. They're the effect. We also refer to them as outcome variables. And in machine learning methods, they refer to them as target variables. So for an example, if I want to know how the weather impacts people's mood, weather would be the independent variable because it is predicting an outcome, and someone's mood would be the dependent variable because that is what we are predicting, what we're measuring. Okay, so the foundation of machine learning and AI is pattern detection. And the goal is to make predictions about future values. The non-automated models that underlie sophisticated models like machine learning and AI tools also have this goal of predicting future values. So think of things like a business wants to predict future revenue. An online newsletter wants to predict future subscribers. Economists want to predict inflation rates, etc. These are all examples of predicting future values. There's two approaches to predict future values, and that is using supervised learning methods and unsupervised learning techniques. Supervised learning methods make predictions about variables that already exist. And we call these labeled outcomes. So, for example, if you have a data set containing patients' height and weight, and you want to make a prediction about their weight given their height, we would consider this a supervised learning type of model because weight already exists in the data set. We have that variable, and we're using what we already know about past data to predict that variable. The dependent variable weight already exists, so it's considered label. So there are several approaches you can take when you are predicting values and several types of outcomes that you can predict. So we have two main categories here, regression and classification. And while both of these types of models predict specific values, classification models at the bottom here, they differ in the sense that they predict discrete outcomes. So think of things like yes, no, true or false, the presence or absence of something, a win or a loss. They're discrete outcomes. Regression techniques can predict continuous variables. So unsupervised models make predictions about unlabeled data. And so by unlabeled data, it's a little bit confusing, but this is variables or groupings that don't inherently exist in the data. They are not naturally occurring. We are not measuring them. So think of, for an online website, like an e-commerce website, think of a customer that you would label as a window shopper. When you open a web browser and you go to a store's website, they don't ask you, are you a window shopper? And you say yes or no. It's not a measured variable, but we can label a shopper as a window shopper using a bunch of different observations. How many pages they scroll through, how much time they spent scrolling, how many different categories of products that they look at, and most importantly, if they make a purchase or not. Based on the pattern between all of those variables, we can then label that customer as a window shopper. And we can use those patterns to predict future customers that may act the same way. And we can classify them as window shoppers. So now that label of window shopper is a new thing that we're introducing. It's unlabeled in our current data set. So things that we could use to get that type of information are considered unsupervised learning techniques. And what I just described is a clustering type of approach, but you can also look at something like dimensionality reduction, which is taking all these observations and trying to find patterns among them to reduce those observations so that we have less data to work with moving forward. I'm not going to touch on unsupervised learning techniques too much just because we have a lot of content to get through, but I did want to make this distinction early on because when you're getting into learning about more sophisticated models, you're going to hear these terms quite often, supervised and unsupervised. So I think that's the general gist of information that you would need to know. Okay, so let's get into sampling. This is another thing I want to get into before we start getting into more sophisticated models. So our ultimate goal when doing most types of analytics, but any type of predictive work, is that we want to predict future values. So how do we do this? We obtain a sample of data and we look at the measurements that we're interested in and we analyze that data to detect patterns within that data set. Inferential statistics, which the slide that we just looked at with the supervised and unsupervised techniques, most things that you saw under the regression category are inferential statistics. I'm going to refer to a few of the models that we go over throughout this workshop as inferential or not. So inferential statistics, we use the patterns that we detected within a sample of data to make inferences about what we expect to see in the broader population. So if I have a data set about people's height and weight, and I want to predict someone's height based off their weight or predict their weight based off their height, the way that I could use that information is if I went out into the world and I randomly selected someone with a certain height, I would want to be able to predict their weight. Machine learning techniques are a bit different. So they essentially automate the process that we just talked about, that inferential statistics goes through, by using the patterns detected within a sample of data to predict values expected to be observed in new, unseen samples of data. So if you can imagine, you have a sample of data, you build a model based on that data. Then you introduce the same type of data, but a whole new data set, a new value. the model from data set A is not going to fit data set B perfectly because it's new data. There's a variability introduced there. It's not going to be 100% accurate, but the model in machine learning then adapts to that new data to try to accommodate this new information so that the models adjust and they will predict high accuracy for now this larger collective data set that we have. And this process just becomes automated. As new data comes in, the model adjusts, and then as new data comes in, the model adjusts. So that is how inferential statistics sets the foundation for more advanced techniques in machine learning. Okay, so now we're going to dive into some really common supervised learning methods. In my personal opinion, if you can understand the methods that we go over here, you can understand the majority of statistical models that underlie machine learning. So we'll start off with a simple linear regression. We have our same three questions. What is it? What do you learn from it? How does it work? So a simple linear regression is a predictive model that falls into the category of inferential statistics. You learn about the nature of the relationship between two variables. So this is different than what we just went over with correlation. With correlation, we were looking at the strength of the relationship between two variables. With linear regression, we're learning about the nature of that relationship. So we learn that from the predicted value of one variable, we can predict what that variable will be based on values of one other variable. And this is just looking at simple linear regression. It's one predictor, one dependent variable. So how does it work? So we have an outcome variable, let's say it's weight, and we want to predict weight using a linear relationship from one other variable, from height. How do we do this? We do this by fitting a line to the data. And then we measure how well that line fits the data, and we also measure the accuracy of this line with the coefficient that we can interpret, which predicts the value of the dependent variable. So the whole fitting a line to data might not make sense right now. We'll go into a visual where it'll help you make sense of it in just a second. But first, let's take a look at the output from a simple linear regression. This is pulled from R. If you saw the title of this workshop, everything is going to be in R, and all of these commands and output will be available to you in a R script that we should be able to get to you within the next few days. So this is a sample data set where we are predicting income from years of experience in the workforce. And so income is our dependent variable, so it's the Y variable. Experience is the predictor variable, or the X variable. So here's the output. What do we look at first? So the two coefficients that you really want to focus on are the intercept and the variable. The variable coefficient is going to be more important for you, it's going to be more interesting than the intercept. I don't know why. I always think it's nice to be able to interpret the intercept, because fun fact, most people don't actually know how to interpret an intercept. They just look right over it. But I think it helps to really ground yourself in what the model's doing. So the intercept is circled in red here, and it's the predicted value of Y if X was 0. So plugging in our variables, it's the predicted value of income if years of experience was 0. So if someone's fresh out of school, this should be all relevant to you guys, fresh out of school, no years of experience in the workforce, based on this data set, the predicted income of that individual is $28,248. Then we look at the coefficient for the variable, for the X variable, which is experience. So it's going to be here in blue. And this coefficient tells us the predicted value of Y for every 1 unit increase in X. So plugging in our variables, the predicted value of income for every 1 unit increase in years of experience. It's important to know how your data is organized in your data set. So what is a 1 unit? In this case, it makes sense. Years of experience, the units are years. 1 unit is 1 year. Data is not always going to be that straightforward. So it's really important to know how your data is quantified in your data set. So how would we interpret this? So for every 1 year increase of experience that an individual has, their income is expected to increase from the intercept value by $2,014. So you would add these two together for every 1 unit increase. If you want to know the predicted value of someone who's been in the workforce for 3 years, times the coefficient by 3, add it to the intercept, and that's your predicted value. So what else do we want to look at in this output? We want to look at the R squared down here. In a simple linear regression with 1 dependent variable, 1 independent variable, you want to look at multiple R squared. So the R-squared tells us the percentage of the variation within our dependent variable that is explained by our independent variable, and it ranges from 0 to 1. So what does that mean? Variability within our data set. Being able to explain it just means that the variability is consistent across those two different variables. They increase or they grow at the same type of rate. And so we can see here a multiple R-squared is 0.9687. So years of experience is a fantastic predictor of someone's expected income. We also want to look at the p-value. So if you've taken statistics before, you probably are very familiar with the p-value. It's basically just saying the likelihood that the coefficient is not 0. So there's a significant effect that we can observe here. Our output, when it's a very, very small p-value, will give you a little like exponent features that I still, to this day, don't really know how to interpret that well. I always have to remind myself. But essentially, this is a very, very, very small p-value. So we can say that this is a significant effect of experience. You'll notice there are two p-values on this output. There's one for the experience variable, and there's one down here for the model variable. Because we only have one x variable in this model, these two p-values are going to be the same. But you'll see that when we increase the number of x variables or predictor variables, the p-value for the model will be different than the p-value that we see for the coefficients up there. Okay, so this is what I was talking about before. Now we can visualize the data to see what we're actually looking at. So there's a strong positive association between years of experience and income, expected income. And you can see this linear relationship. So when I was introducing simple linear regression, I said that we were fitting a line to the data. So what does that mean? So R will look at the data, figure out the line of best fit. We'll essentially get a slope for the line of best fit. And when we plot that line, it looks like this. And the data points fall like perfectly on this line. And so another way that we can measure how well this line fits the data is by looking at the residuals. So they're gray. You might not be able to see them too well, but there are little lines from each of the data points to the regression line. This regression line is essentially just telling you if you gave, let's say you're looking at someone with 5 years of experience, how much income should I expect that they would make? Just follow it to the line and find the point. So this is our expected value. And because the data points fall very close to this line, this is a pretty accurate model. Let's look at a different data set though. So this is same data set, but we're looking at different variables. So now we're predicting income from someone's age. So I don't have any of the values highlighted or circled here. Does anyone want to give a crack at how to interpret this output? Anyone feeling bold? No. Okay, so for the intercept, right, that's the predicted value of the outcome if the predictor variable was 0. So someone is 0 years old, fresh out the womb, we can expect they'd make $22,975. Now you can kind of see why people usually don't look at the intercept that much, because for values like this, it's so silly. It really is not meaningful. What we care about is the coefficient for the variable, so for age. So for every year that a person ages, they can expect to make $447 more. The age variable is significant to the point the p-value is less than 0.05. So there is a less than 5% likelihood of us observing this pattern within the data set, so that we take that as sufficient evidence that there is a meaningful relationship between these two variables. We can see down here that the multiple R squared, 0.28, that's pretty low. And so the model fit isn't great for that. And so you're looking at this variable, you're like, well, it's a significant predictor, but the multiple R squared is saying it's not a good fit. Let's look at the data. It's not a good fit. Like, there is a linear relationship here, but it is so not straightforward. And when we try to fit a line to this data, it does not look like it did in the last data set. That's because there's more variability within this data set. And we look at these residuals, they're much larger than we were looking at with having years of experience predicting income. And so we describe that difference within, I'll go back, this difference between the data points and the correlation line, or I'm sorry, between the data points and the regression line, are the residuals. And we can compare the fit of a line to data side by side, and seeing that this second predictor of using age as a predictor for income compared to using years of experience as a predictor for income results in much larger residuals. And so we consider this a loss. So the first data set here, the line has a much better fit for the data. It's more appropriate, it's more predictive. And then for when we're looking at age, the fit is not as good. And so we can see that with the larger residuals. So the reason I bring this up now is because this is going to be a common theme that when we're trying to build a machine learning model, we want to reduce this. We want our line to fit our data as best as possible. And so this is a really good example to see early on of a good fit and a less good fit. I don't want to call it a bad fit, but a less good fit. And so this is the difference between these two is what we consider loss, which is quantifiable. We can attach a number to the loss. Okay, so now we're going to get into a new type of analysis, multiple linear regression. And it's essentially the same thing as a simple linear regression, except we are increasing the number of predictor variables in the model. So it's the same type of model. It's a predictive model, falls in the category of inferential statistics. In this case, we're learning about the nature of the relationship between one outcome and multiple dependent or predictor variables. So how does this work? We're still going to use a linear model, but instead of fitting a line to the data, we're going to fit a plane to the data. And I will show you an example of what that looks like. But because we're adding extra dimensions within the data, we're basically adding different axes. We can no longer fit a two-dimensional line. We have to fit a three-dimensional plane. And then we can quantify how well the plane fits the data set, looking at the same type of metrics that we were looking at in the simple linear regression. So this is the output from multiple linear regression. The formula is essentially the same, except we're adding in predictors. So this is a different data set. For this data set, we are going to be predicting the prices of homes from the square foot of the living space, the number of bathrooms in the home, and the number of bedrooms. And so to add, we just add plus signs, and we add these predictor variables in R. And we look at the same things. So for the intercept, same thing, predicted value of y if all x's were 0. So it's the predicted price of a home if there was no square footage, there were no bathrooms, and there were no bedrooms. Again, in this case, not that helpful for us. The variable coefficients are slightly different than the simple linear regression. They still note what the predicted value would be for every 1 unit increase in that x variable. However, it's contingent on holding all other predictor variables constant. So all other predictor variables do not change values, and this is the expected increase. So for this example data set, square foot of living, if we're looking at the coefficient here, it's 309 and some change. So how do we interpret that? For every 1 unit increase in square footage of a home, we can expect the value of that home to increase by $309 if the number of bathrooms stays the same and the number of bedrooms stays the same. You always have to add that in to your interpretation of regression coefficients. And we do the same. So if you took a sneak peek at the coefficients, you might be like, what on earth is going on with bedrooms? How come it's negative 57,000? Think about it. Because this is if a unit increases. So if you're saying, basically what that is saying is if the number of bedrooms increases, the value of the home goes down. And it's because we're holding everything else constant. So if the number of bedrooms is going up, but the square footage is staying the same, what's happening to those bedrooms? That means they're getting smaller and smaller. And so the value of that home is not going to be that much if you're making the bedrooms teeny tiny to the point where they're no longer a comfortable living space. And that's why it's really important to keep the other predictors in mind. Also really important to carefully select what predictors you're putting in a model. And I'll note now, because we're talking about what is appropriate, what's not appropriate, there are assumptions underlying all statistical models of what type of information is appropriate to be putting into a model. And one of those is having a linear relationship between those two variables. And there's a bunch of other assumptions that we would be here for 5 hours if we went over assumptions. But just be aware that to even run these types of analyses, there are some certain assumptions that need to be met. Okay, back to the output. So instead, now we have an additional metric here, the residual standard error. So the residual standard error down here in orange measures the overall accuracy of the model, and then you can use this value to compare the fit of this model to other models. So it's a really good value to kind of extract from your output. If you have been exposed to more advanced statistical models or machine learning models, you might have heard of the term RMSE, the root mean squared error. as a way to evaluate the fit of a model. It's essentially the same thing as a residual standard error. The residual standard error, they have different denominators. So the residual standard error accommodates for the addition of these variables. If you've heard the term degrees of freedom back from your statistics course, it's probably bringing back like bad memories of trying to figure out what those are. But the more information you put into a model, you need to account for that in your calculations. And you usually do that within the denominator. So the residual standard error, same thing as the root mean squared error, but the denominator accounts for the degrees of freedom that results from adding in additional variables. We have an R squared for multiple linear regression, but this time we're not going to look at multiple R squared, we're going to look at the adjusted R squared. You interpret it the exact same way. It's still the proportion of variance explained by the model. So here about 50% of the variation in the price of homes is explained by the square foot of living, bathrooms, and the number of bedrooms. We look at adjusted R square because same thing with the residual standard error, we have more variables in our model, and so we need to account for that. These two variables or values of multiple R squared and adjusted R squared should be pretty similar. You're only going to see a real big difference if you're adding in like a ton of predictor variables. Just keep in mind that you do need to adjust how you interpret the proportion of variability or variance explained depending on how many variables you're putting into that model. And then p-value is the same as before. We interpret it the same way. But now you can see that the p-value is different. It is actually the same p-value as square foot living. That's not planned or anything. There's no association there. It is just by happy chance that they happen to be the same p-values. And for number of bedrooms too. But they are interpreted all individually. Okay, so I said we were going to look at a plane. This is the plane. I did not want to make my own visualization hand up. I was being really lazy and I didn't want to fit a plane in R, so I found this from the internet. So this is different data. It's looking at systolic blood pressure being predicted by age and weight. And so you can see that we have a typical x-axis here, and then we have a z-axis going up of weight. And so now we have a three-dimensional figure. And so instead of just fitting a line, we have to extend outward to accommodate for that additional variable. So now we have a plane. But you interpret it the same ways. You have all of the different data points. You have the plane of best fit, and then you can see residuals. They're quite a lot. The residuals are quite large within this data set. But the way you interpret it is exactly the same as you would with a simple linear regression. Okay, so what do we do if the data is not linear? So this is an assumption of having to run a linear regression, is that you have to have a linear association between the two variables. So what happens if you don't? This data set is predicting effectiveness of a drug from the dosage of that drug. And if we were doing the approach that we had just adopted, we're like, let's fit a line to this nonlinear data. If you forgot to look at the data first, or you forgot to visualize it first, you just fit a line blindly. It's terrible. That does not capture the pattern going on within this data set. And if we look at the residuals, they're massive. And so this line is definitely not appropriate for this data. So what can we do? Visually looking at this data, there's not that many observations, so this is we're able to do this. We can see they're kind of like four groups of data points within this figure. So a way that you can conceptualize this data is that there's some type of meaningful relationship between these groups. And if I didn't group them together and I treated them as if they were linear, and I had the line of best fit that we just plotted, the reason why we can't treat this as linear and run this type of regression is because if someone's given a 20 milligram dosage and I have to predict what I think is going to be their chances or the chances of the effectiveness of a drug, according to a linear regression line, I would guess, around 37% effectiveness of that drug. Looking at the pattern of this data, we know that's incorrect because right here around what the 20 milligram effectiveness is 100%. That's a huge inaccuracy to be able to report to someone that 30% chance effectiveness when actually it's 100%. And so we have to be able to accommodate for this difference in the way that we're interpreting this data. Okay, so what can we do? A regression tree. So if you've heard of decision trees before, there's actually different ways that you can look at decision trees. One is through regression, a regression focus. The other is through a classification focus. So right now we're going to focus on regression. If you remember back to the beginning of the workshop, What's the difference between regression and classification? Regression is predicting a continuous outcome, whereas a classification is predicting a discrete outcome, a yes or no, true, false type of outcome. So without getting into the math behind a regression tree too much, essentially what it does is it finds a node that splits the data up the best. And it basically says, so for us in this data set, there's math behind it that I can explain, but this data set is essentially saying that this 13 milligram dosage right here is meaningful. There's something about getting less than that dosage and getting more than that dosage. And so we split it, the data set, up by that. If the dosage is less than 13 milligrams, we could take the average of the values in this square, which is 4.5% effectiveness, and that's now our predicted value. That's what we're going to predict for this group of individuals. If they're not getting a dosage that's less than 13 milligrams, well, is it greater than or equal to 31 milligrams? This is the next branch, the next node. And we take the average of these values. If it is greater than or equal to 31, the drug is expected to be 2.5% effective. So basically saying if you fall within this group. And this continues. And so then we get to the very end. If it's not greater, well, is it greater than 26? So then it would fall into this category here. If it's yes, it's 54.8% effective. If it is not greater than 26, it has to fall into this group, and it's 100% effective. You do not actually do this. R or any statistical programming language that you use will conduct all of this, but essentially it takes every single data point and it will measure the distance from the average of all the data points, which is this blue line here, and it tries to minimize the collective distance, or the average collective distance from all the data points to that line. And so R told us that the best way to separate the data right off the bat is using this 13 milligram unit up there. So we refer to this as the root node. And so there's a lot of math that dictates behind how you can create these nodes. But this is another way to predict a value that doesn't have that inherent linear nature to it. Next up, logistic regression. So it's very similar to what we were looking at before with simple linear and multiple regression, except it's predicting a discrete outcome, a binary outcome. So what do we learn from it? We learn how much the predictor variables contribute to the log odds of a discrete outcome. And how does it work? Again, predicts a discrete outcome with the best accuracy possible. And it calculates the probability of each point in a data set being 0 or 1, and then it feeds it into this logit function. So this is the output of a logistic regression. For this data set, we are predicting admittance to a college based on GRE scores and GPA. So the outcome is accepted or not accepted, binary outcome. For the intercept, we interpret that to be the log odds of y if all x's were 0. So the log odds of someone getting into college, if their GRE and GPA was 0. So obviously it's going to be negative. So for the variables, we interpret it as the predicted change in log odds of acceptance into college for every 1 unit change in X. So 1 unit change in GRE, as long as GPA stays the same, and then for every 1 unit increase in GPA, as long as GRE scores remain the same. The null deviance and residual deviance values down here tells us about the fit of the model. And so how you interpret it is that you want a larger difference between these two variables. The larger the difference, the better fit the model is. Our values here are 499 and 480. That's not a very big difference, so this is not a very good fit. This model is not a very good fit for this data. And we also have the p-value here that tells us how significant these independent variables are when predicting the outcome variable of admittance to college. Okay, so we're going to get into random forests next. Just want to put a note. I think you're going to ask the question I was about to say. Go for it.
I'm not sure if I am, but how do you know when to use the logistic regression versus the multiple linear regression if you're using GRE and GPA similar to the other example of multiple variables?
That's a good question. So it's the outcome. The outcome is binary here. It's yes or no, accepted or not accepted. When you're doing a simple linear regression or a multiple linear regression, the outcome you're predicting is a continuous value. So I'm predicting the price of a home. That can range from 0 to 28 million. That's a continuous variable. Good question. I thought you were going to ask, how do you interpret log odds? Don't ask me, I don't know.
Okay. Alright, so now we introduce a new model called random forest. So we have seen our decision trees, and we have a sense that decision trees is very powerful. So then the intuitive question is, well, would it be even more powerful if we not only grow one tree, but many trees, right? The answer is fortunately yes. And we'll tell you the reason why it is more powerful later. But let's just bear with me, take this as an assumption, like we believe that many trees will be more powerful. And this is how you build a forest. You don't really need to understand the algorithm China because most of the existing packages will take care of them. But just give you a sense how this forests have grown. First, you need to choose how big your forest should be. This is the parameter B. And for each tree, you want to grow trees. And for each tree you want to grow, you draw a bootstrap sample from the data. So if you know the concept of bootstrap, basically you shuffle all the data into a bag and you take one out by one after another. And that's like sampling with replacement. And you construct a different sample that's different from the original sample and build a tree on this bootstrap sample. And you train your model, your tree on that bootstrap sample. But at each split, we do not use the same variables. We choose a different subset of samples, a subset of columns, subset of features to do the trees. The purpose of doing this is to decrease the correlation between trees. Why do you want to do that? I'll tell you later. But that's a big feature of random forest, is to decrease the correlation between trees. And we output a collection of trees in this forest. We have B trees, so it's a forest of size B. And how do we make predictions? Right? If it's a regression problem, as Jamie just said, we want to predict the value. We want to predict a real value. We just take the average of all the trees' predictions. Right? Each tree will have a prediction with its value. We take the average of all the trees. And in this classification, let's see, like we have B trees, maybe half of them predicts A, half of them predicts B. Whatever more trees, whatever the tree, which group is larger will take their side as a majority vote. So that's how you use a random forest to make predictions. So we'll revisit this later, but now we have many theoretical knowledge, right? We are very itchy, want to actually use our knowledge to do something. Let's do something. Let's build a model to predict a data set, a fictitious big data set built by me. So the goal is to predict GPA using a student's favorite color. This is what I call scientific fortune telling. You imagine how useful that model is. You give me an answer, give me a color, I will tell you how well you will do in your final exam. Very useful, right? So now suppose we have a data set of 4 data points, right? And it looks like this. So horizontal axis is a students. We have 4 students. The student's favorite color. The first student's favorite color is blue, and their GPA is 1. And the second student's favorite color is yellow. GPA is 4, and red 1, and green 3. These are our data sets. So one might be a good model to predict this relationship. I'll give you 2 candidates. First is this dumb linear regression, right? It's not linear, obviously, but let's just feed a line. And we can measure how poorly this model fits. So the empirical loss measures how poorly this model fits the data we observe. And the empirical loss is 1.57, calculated by me. And the right-hand side, let's just do this crazy model, right? So it's very complex. Let's connect the dots, right? Let's connect everything. It has perfect prediction, right? Whatever you input will tell you the answer exactly correct, right? So empirical loss is 0. It doesn't have any loss. There's no residual. So which one is a better model here? Take a guess.
First one.
First one? Does anybody believe the second one is the better model? No? Wow, I'm surprised. Okay, so because our goal is to predict data we haven't seen, right? So let's take another sample from this distribution. The same distribution, same group of students. There are 4 different students, right? The students, these are their favorite colors, and the y-axis is the associated GPAs. And let's evaluate how our models perform in this new data set. So here's our dumb linear regressions. Now this doesn't change much. The empirical loss is still 1.6. Originally it was a 1.5, increased a little bit. But you can see our fancy model, like most flexible model, actually performs very poorly. It's almost 4 times larger in terms of the loss, right? The loss. So it's obvious because this data set was very different from the original data set we have, right? For the blue students, now the GPA is 4. Originally it was 1. And for the yellow students, now it's 4. Now it is 1. Originally it's 4. Right? This new data set looks very different from our original data set. So even though our original model fits very well, if it predicts poorly in this new data set. Why, right? Recall that the only criteria we have in our previous model building process is that we want to minimize the in-sample loss or error, right? We want the model to face the data observed very well. But if that can lead to this like catastrophic outcome, what are the criteria we should embrace, right? How do we train a model if these can happen? Right? That's kind of the question. So to answer that, we need to introduce the concept of bias and variance, and this very famous thing called a bias-variance trade-off. So bias is basically captures on average is your model correct, and then the variance is if you have multiple samples, right? You have a population, you don't observe the entire population, you only have samples from this population. If you have different samples, how does the model change across different samples? If it changes a lot, it means like the model has a high variance, otherwise it has low variance. And I'll tell you a rule of thumb. It's a kind of a canonical wisdom in the literature. If the model is more flexible and the connecting dots, it's very powerful, complex, it will have lower bias, but it will have higher variance. If it's less flexible, it will have higher bias, but like a line, it will have higher bias, but lower variance. And to predict well, you need to balance both bias and variance. Right. So maybe it's easier if I give you some visualization. So I draw a picture here. Like suppose this is the data set. So the true relationship between x and y is a curve. Right? So something like this. Right? Then you can, like if you fit a line, it's almost flat. But if you're in a new sample, the same relationship, but it's just three different draws. So it may look like this. And the true relationship is this. Right? This is like this part, and this is like this part. If you fit a line in this graph, it will still look like this. The model doesn't change much across samples, even though they look different, but they are from the same line distribution. But if you use the connect the dots model, well, they look very different, right? So it will look like this. So it will look like this in this sample. So this has low variance. It doesn't change much across different samples, and this has a high variance. There's a little bit change in your sample points. The model changes drastically, and prevents you from making consistent predictions. But this have high bias. No matter how many points you have, it will never recover the true relationship with it reaches this curve, right? You can only fit a line. You can never fit a curve using linear regressions. So the bias here is high, but it's possible for this model to actually recover this curve. As long as you have more data points, it's possible you can make this smooth and recover the true relationship between x and y. So this is the bias-variance trade-off, right? So you have high bias, then you have if you have high bias, you have low variance. If you have low variance, you have high bias. And to predict well, you need to balance both. Yes, okay. So let's recap this problem. So linear model is simple. It's basically one of the simplest model you can build. Then it's less complex. It means you have high bias. If the underlying data generating process is not linear, you force a line into a non-linear relationship. So the bias will necessarily be high. But it's not complex. It's very easy. It doesn't change across samples. You will capture the general trend in your data, and that general trend will always be true across samples as long as the samples are from the same line distribution. But if you look at the right-hand model, it's more complex, right? You can do very well, like fixed data, fixed sample, but it will change a lot. It will vary a lot across samples. So there's no guarantee that if you draw a different sample, the model will perform as well. And this is why the right-hand side tends to overfit. So the more complex model will overfit the data. Overfitting means the model captures idiosyncrasies of the data set. We want to capture the general trend, not idiosyncrasies, because idiosyncrasies change a lot drastically across samples, and we do not want to capture idiosyncrasies. But because the model is so powerful, you can capture very detailed like natures, detailed like features of the data set. It can overfit. It tends to overfit very often, right? That's what we want to guard against. And to guard against overfitting, we do not only have one data set, we have two data sets. We have a training set that used to train our model, and we have a test and validation set to evaluate the model. Usually it's from the same distribution, and it can be not from the same distribution. But like that's not so important. But usually it's from the same distribution. We have a large data set, we cut it. One portion of it is used for training, one portion of it is used for testing and validation. And we measure model performance on both sets. And here is the very classic curve, training, testing, error curve. This is a horizontal axis is how complex your model is. The more complex, the performance in your training sample will be very good. At some point, it will have zero training error, as our previous model indicates. It will just memorize your training sample very well, never makes an error in your sample. But the problem, we don't care about training sample, right? We want to predict data points from the samples we never see. That's the whole point of making prediction models. If you have all the data you need, why do you make predictions? You already observe all the outcome, right? So we only care about test sample. In the end, we only care about test sample performance. So, but if you make the model too complex, given a fixed training set, your test sample actually will increase in the end. So the sweet spot is somewhere here, right? So it's the lowest point of your test error curve. So monitor both loss. If the test loss increase, maybe do not stop increasing the complexity of models. But if the training error and test error both go down, probably it's better to increase the model complexity because you are in this region, right? You are underfitting data. You can make them do better by making the model more complicated. Good. But I want to stress that that's not always true. It's not a theorem. It's not proven. So recent discussions have shown that our classic wisdom is the left-hand side family, right? The training error goes down, but test error might go up. But if you look at crazily large neural networks, that we'll observe something on the right, similar to what was on the right-hand side. It's possible if you increase the model complexity to some crazy level across this threshold. It's possible if it's possible to observe that both the training error is a zero. You basically the model memorize all the training data, and at the same time, even after you increase the model complexity after this point, the testing error can still go down, right? So there is no bias variance trade-off across that point. That's an interesting threshold observed by recent research, and I'm not sure people really understand why. So basically, this is an inductive conclusion. We observe something interesting, we generalize it, try to make it a theorem. But there might be new things popping out, and we may modify this conclusion later when we find more interesting things. Okay. All right. So, the bias variance trade-off applies to the vast majority of the models we'll use. In our daily common popular models, this trade-off still applies. Then if we want to use more complex models, we of course want to use a more complex model because they're cool, right? So we don't want dumb lines. We want more fancy, flexible curves. And intuitively, more flexible models have fewer assumptions. Why would a model with fewer assumptions perform poorer than a model with more assumptions? That's just counterintuitive, right? Intuitively, more complex models should work. Then how do we improve more complex models' performance, given we know that the bias variance trade-off holds? We can have more data, right? More data, a larger data set supports more complex models. Or we can reduce variance, right? The problem with complex model is that it has low bias, which is good, but there's very high variance. If there's a way for us to reduce the variance while keeping the bias low, then we get the benefits from both worlds. Then how do we reduce variance, right? We can take averages, right? The important property of the sample average from independent draws is that the variance of the sample mean is only a fraction of the variance of the sample, and the fraction decreases with your sample size increases. And n goes to infinity, sample mean doesn't have any variance. So it's a good property of sample variance. So can we use this to decrease the variance of complex models? That's exactly what we're doing for random forest. Right? Each individual trees have low bias, but it has very high variance. It's split arbitrarily. And if you give a very slightly different data set, it's split completely different. Then how do we reduce this variance? We just draw a large collection of decorrelated trees. So the property, this property only holds. This formula only holds for IID draws from the population. So we want to reduce the correlation between trees. so that the formula I just showed you still holds. And then by building this large collection of decorrelated trees, we preserve the low bias property of decision trees. And at the same time, we significantly reduce variance by a factor of 1/n. That's a significant reduction. That's why random forest usually performs significantly better than individual decision trees. Right now? Okay, so now you know how to build AI models, right? You learn how to use training and testing data to build complex AI models and machine learning models. This is exactly what they do when they build large language models, large vision models, or whatever models you want to use. This is exactly the pipeline. So you know the pipeline. You just don't know how to use the models yet. You can learn how to use the model in our other workshops and utilize this pipeline to build your own fancy AI models. Okay, I'll return the stage to Jamie, and we'll talk about unsupervised learning.
Thank you. So I'm not going to go over unsupervised learning methods in too much detail. There will be an R script. I'm not sure if I mentioned this in the beginning. There will be an R script that's available to you all for registering for this course. So I will try to put in some type of code for unsupervised learning methods. But just to go very high level of what unsupervised learning methods are, like I said before, it's trying to predict unlabeled data. And so you have these data points that exist, and you can see there's some type of like organized nature to them. And so one method that you can apply is a k-means clustering, where your software will identify how many clusters make sense for your data set, and then you also have to put in your expertise to validate that that number of clusters is appropriate for your data, and it will bring them together and make these distinguished groups. And then you have to go in and figure out what is different about these groups. Why are they clustered together? What are some commonalities that they have? And then you can assign a persona to those clusters based on the observations. Then we also have principal component analysis. PCA is a form of dimensionality reduction. And so I kind of alluded to this in the very beginning. You have all of these data points, and this is when I think of PCA, I think mostly of like survey responses, where you have like a lot of data sets and you're like rating certain responses to things. And you can see how people tend to respond to the same category of questions similarly. And so you can group those categories as like one assessment instead of 15 different questions for one type of assessment. So you're reducing the dimensions within your data set. And this is kind of visually what it looks like. Like I said, everything available to you today, all the visualizations that we have created will be available in an R script. So if you want to go run them yourself or kind of mess around with them, see if they break, how you can fix them, that's always a really good learning strategy in R. With that, I will open it up to Q&A. Any questions?
Could you explain again the difference between the adjusted R and the other?
Yeah, the multiple R squared and the adjusted. Yeah, so multiple R squared, it's actually backwards. I should have noticed that, or noted that earlier. For simple linear regression, you look at the multiple R squared. For multiple linear regression, you look at adjusted R squared. Why they named them that, I have no idea. Multiple R squared is the most straightforward way to assess the percentage of variation that is explained in the dependent variable by the independent variable. The reason why in multiple linear regression we look at the adjusted R squared is because we have more predictors in the test. So this is going into a whole background of adjusting your analyses, but in all different types of analyses that you can run in the world of statistics, the more variables you are introducing into an analysis, you have to adjust for that in your interpretation. And so sample size will determine that, and then you kind of like subtract every variable that you include that will be reflected in the degrees of freedom. So if you look at the degrees of freedom for a multiple linear regression compared to a simple linear regression, they'll be different because they're taking out variables that they're using and they subtract those variables from the degrees of freedom. The degrees of freedom are the denominator when you're computing something like the R squared. And so you're just gonna have a difference that's just accommodating for the increased number of variables or pieces of information in that model.
Okay. And you want them to be close? Or
they're usually going to be very close. If there's a big difference between them, it's because there's a very big difference in the number of variables you included in the model, so the number of predictor variables. We didn't get into it. There's also another class of regression, multi-factor regression. So you can predict multiple outcomes, and that just gets into a whole other domain. But you can compare the amount of variables in it using the differences between those R-squared variables. Any other questions? Awesome. Oh, go ahead.
When would you use the random forest approach? Like, why would you use it specifically versus, say, like a multiple regression analysis?
So random forests are able to capture the nonlinear relationships. So it's much more powerful than OLs, but usually it requires more samples as well as we just discussed.
Is there a question right there?
Yeah, like can you explain more about the example on the whiteboard? Like which method is better? Is fit in the line or just connect the points?
Yes. Okay. It's unclear which one is better. So this is a trade-off here. The trade-off I want to say is that if you have limited samples, like given the sample size 3, right? If you choose a more complex models like this, right, connecting the dots, so that one. So you are risking overfitting. Right? You fit this data set very well, but if a new data set from the same distribution you collect, it will perform terrible, bad, right? Very not good. But so in this case, we might want to sacrifice some sample model complexity for a stable prediction. A stable prediction means the prediction doesn't change across different samples. Right? So in this case, in a sample size of 3, I would suggest you use a linear model because the model makes consistent predictions. It can capture the overall general trend in your data set while not trying to overfit the data. If you use a more complex model, unless you do you can do a train test split and you train a model on data set. This is a training set, this is a test set. Train the model on this training set, test it here. You can observe whether your model performance on this new data set is as good as well as your previous training set. Right? If they're all good, you all can use this model. But if it's not as good, try a simpler model. Usually the simpler model gives you a more consistent performance. And if you observe that yes, it's true that in both training and testing set your simple model performs better, right? Than your complex model, then use a simple model. Basically, we have made a case for using a simple model over using a complex model. It is possible that a simple model performs better than a complex model, even though the complex model seems more flexible, right? Should be able to capture data patterns and detect data patterns much better. But sometimes it's the case that we prefer simple models.
I see. But is there a way like we can find the model between the simple and the complex one?
Yeah, so there's a huge literature on model selections, right? You can gradually grow, right? Currently, it's the simple model, right? You can say it's x beta, right? That's a linear model. You estimate beta. You can gradually add polynomials, right? X squared, gamma, right? Delta, x cubed, something. You can add it. It goes to a long list. They can stop at some point. Say, okay, like here, this point, I think is a sweet spot. After this, it's too complex. The data doesn't support such a complex model, and there are many other models you can gradually grow, including trees. Right? You can make it a very deep tree, or you can make it very shallow trees. You can gradually grow the trees based on how you observe its performance on your test samples.
Gotcha. Thank you.